Right. Hi, everyone. My name is Karl. I'm a researcher at ETH Zurich. I'm going to be presenting ZLiTE, which was a project to get lightweight clients for shielded transactions and where we leveraged trusted execution environments. This is work that I did together with all the people that are listed here. So first, let's look at what Zcash, or some properties of Zcash. I guess all of you know what Zcash is. And one of the main parts that differentiates Zcash from other cryptocurrencies is the strong privacy that it offers. So we have these shielded and transparent transactions, but we have the drawback that for shielded transactions, which are the transactions that actually give us this privacy, we have really heavy client requirements. So for example, creation of shielded transactions is computationally expensive. It's got much more efficient with sapling. But clients still need to download and process the entire chain. So in order to figure out whether a shielded transaction goes to you, you need to download every transaction, try to decrypt it, and see whether it actually belongs to you. And this has the consequence, on one hand, that most transactions are still transparent, and there is no mobile client that actually supports shielded transactions and uses some lightweight client mode in a privacy-preserving way. And this is exactly the part that we wanted to handle with this. So for lightweight clients, we have different options. Lightweight clients in general, the idea there is that we have clients that don't need to be a full node, so we can only download small pieces of information. Ideally, we download the transactions that are of interest to us, and then maybe some additional information that we need to verify this. So in Bitcoin, we have this SPV approach, which stands for Simple Payment Verification. And this works directly for Zcash if we use unshielded transactions, but of course it doesn't work for shielded transactions. So if you want to do something similar for shielded transactions, we actually need to send the viewing key somewhere to some full node that decrypts transactions for us and then only forwards the ones that we are interested in. And that's of course not ideal because with that we lose privacy. We can, however, use trusted execution environments on these full nodes. So we can have these isolated execution environments that we can send the viewing keys to. And this makes the whole thing much better. There are still some issues where we need to consider potential leakage. And we still have the problem of sending transactions, because in order to send a transaction, we need to get the witness in the node commitment tree at the point when we are sending a transaction. So we somehow also need an update mechanism for this. We could go even further by basically just putting everything into a trusted execution environment. However, if we also put our spending key there, that means that in case there is some break of this trusted execution environment, then we also lose funds. In the other case, where we don't send the spending key there, then the worst case is we lose privacy, but we still won't lose any money. So I've been talking about these TEs now. What actually, so we should only use it for privacy. But what is a trusted execution environment? So in general, if we have some software running on a system, we have different applications. Those applications rely on some operating system. And then at the bottom, we have hardware, CPU, memory, and so on. And if we now want to run something in application 2, we need to trust the full stack. If one of these parts is compromised, then our application is compromised as well. So this means that in the case where we want to send our viewing key somewhere, if the operator of the node is malicious, then the OS has to be considered compromised, which means that we lose all of the privacy. Now what trusted execution environments give us is sort of an isolated part of the app, so we can run a part of this app in a so-called enclave, which isolates it from the rest of the operating system. So this means that the only part of the platform, of the hardware that we have to trust is the CPU, because we have keys that stay within the CPU that are used to encrypt the memory of this enclave. And we can also use keys to store data on disk. So we encrypt data, can store it on disk. And all of this is, as long as the CPU is not broken and there are no additional vulnerabilities, this is basically completely isolated from the operating system. The operating system cannot change the execution flow, it cannot read the data, and it cannot influence the integrity, so it cannot change the control flow either. Yeah, so these are kind of the basic properties that we have. So we have this isolated execution. Sealing means we are able to store data on disk. I've mentioned this before. And then in addition to that, we also have remote attestation, which is actually quite important, because if we only have this system, but we cannot verify that that's actually running there in such a trusted execution environment, somebody could just run it outside such an environment and still give us the data, but read everything. So remote attestation gives us a means to verify that the correct code is running in such an execution environment, and that allows us to actually trust that if there are no vulnerabilities, everything that we do in there actually stays private. So how does our system work? So basically we have on the right side, this is just a Zcash network with all of the full nodes. And then what we did is we modified such a full node to add some part that is run in this secure enclave. So if you look at the detailed view, we basically have all of the original functionality, but then we add the secure enclave, which is basically used to serve data to clients. And the lightweight clients connect to this enclave. They receive data from there. They receive the transactions that they're interested in. And then they can do the same as we do with SPV in Bitcoin, and basically get the same guarantees for integrity of these transactions, but we also keep the privacy that we get from the shielded transactions. How does this look in detail? So basically the client starts by getting block headers from the peer-to-peer network, and he can use those to verify the proof of work. The client can verify that he's on the longest chain. Then he connects to such a ZLiTE full node and performs remote attestation with that node. And this gives him the guarantee that the correct code is running there within this enclave. Then we have a step for authentication. This basically just sets up a secure channel. So we use TLS connections to actually connect between the client and the server. So and the TLS connection ends within this enclave. So all of this communication is encrypted. And then the client, over this established connection, he sends an information request where he basically sends his viewing key, and he sends the latest block height to which he's synchronized. And that will tell the server to give him the data starting from this height h up to the newest block. The full node then basically scans the blockchain for transactions that can be decrypted with this viewing key, and he puts these transactions into a response. And this response is then later sent back to the client. Now, one large issue with this that I've mentioned before is that we have potential leakage. So even with such a trusted execution environment, the operating system can still observe quite a lot of things about this. For example, if we write to disk, the operating system will see what part is written to. It can observe some memory accesses, and depending on the protection mechanisms that are available, he could even run side channel attacks. So we can potentially observe a lot of information about the control flow within this enclave. And if this is not designed well, then you can lose basically privacy, because you can run attacks that will get you the viewing key. Or you can figure out which transactions are put into the response, which allows you to link transactions together. So in order to put these transactions into a response, we actually create a so-called ORAM, which is a mechanism that basically randomizes the location where something is written to, and you don't see whether you write or you read. And that way, for every transaction that is put in there, we don't really know where it's stored. And we do this for every transaction obliviously. So for every transaction, we see such an ORAM operation. So it's not that we have a check. If this transaction is interesting, we put it into that ORAM. But we basically do this, we have the same control flow for every transaction. In order to do this, we use another kind of low-level primitive that replaces some of these conditionals that I'll mention a bit later. And that basically, since the same operations are done for all of the transactions, we don't see which transactions are actually put in that response. That response is then collected and sent back to the client. In addition, we also send a so-called node commitment tree update that I'll also come to later. The ZLiTE client can then verify proof of work, can verify transactions and witnesses in the Merkle tree to make sure that these transactions are actually in some block, and so on. And he can apply the node commitment tree update to the witnesses of the node commitment tree of his outputs that he owns. So I mentioned some protection against leakage. So we have this ORAM for the response. And then in order to replace these if statements, we use a technique that is basically a wrapper around a conditional move instruction. And this performs basically a move for every, instead of having an if condition where we say, okay, if this happens, we move source to location. We always read from source, and we always write something to the destination, but depending on whether the condition is true or not, we might write the same thing or we might write a different thing. And this basically makes sure that every source is read, every destination is written to, and the control flow is the same independent of the conditions. And this removes a lot of potential for side channel attacks, because even if the operating system would be able to see the full control flow, you wouldn't learn anything from this. There are potentially still other side channel attacks that are unknown, but for this kind of digital side channel attacks, this is a known technique, so it's not a technique that we developed. This is something that we took from previous work and applied selectively to the parts where it actually matters. And also the response size is independent from the number of transactions that actually match, and it's only dependent on the number of blocks that we scan. So this means that there is an upper limit to the amount of transactions that we can get sent back, and this is something that can be determined empirically what kind of range makes sense there. Now I've mentioned this transaction creation that we still need to be able to do. So for transaction creation, in order to create the proof for the inputs of a transaction, we need the witness in the current no commitment tree for the transaction inputs. One way we could get those would be to connect to this node and just get the witness when we want to send a transaction. However, that opens up new issues for privacy. because in order to actually compute this this witness for like a single output, so if we request, please get me the witness for this output, we either do straightforward computation for this, but this makes it very easy to observe leakage that allows us to basically figure out which output that was requested for. Or we do the same thing obliviously, which means that we apply the same sort of techniques that we've used before, but that would be extremely expensive because we basically need to do this for all transactions. And that's why we use a mechanism to update witnesses. So if at one point you have a witness for all of your outputs, it is enough to receive an update for the scanned interval, and you can apply this to all of the witnesses and basically get an up-to-date witness with this. And this basically looks a bit like this. Not sure if the pointer works. Yeah. So basically, if we assume that at some time t1, the node commitment tree is filled up to this position here, and we have some output that belongs to us. So in this case, it would be output C. Then we have a witness for that point in time, and that witness would consist of this node D, then the node N8 here, N5 and N3. And if we now scan blocks for the time interval T1 to T2, we can receive an update that consists of always the right child of every node on the path from the first node after T1. So in this case, this will consist of this node here, N11, N5, and N3. And once we have these nodes at time T2, we can simply replace the nodes from our witness that we had before for time T1 with the new nodes that we received at time T2. Because all of the nodes that will change in this tree are actually part of the witness. And all other nodes that are part of the witness will remain the same because they're on the left side of the tree. So we still have, as part of the witness, we still have the node D, we still have the node N8, they remain unchanged, but then we replace this node N5 and the node N3 with the new values from this node commitment tree update. And this works for all of the outputs that have been included at any point before time T1. And with this information, we can then basically create the proofs that we need to spend the outputs, and we can do this inside the client, and then broadcast this to the peer-to-peer network. So quick note on the security of this. So this is because we use this trusted execution environment, this is protected against malicious operating system. We add quite a lot of side channel protections. So for known digital side channel attacks, such as cache attacks and so on, we have protections for this, which means that the leakage is reduced to a very, very small minimum. And even if the trusted execution environment is broken completely, so if somebody does an invasive attack where you somehow extract the key from the processor, if there are new attacks such as Foreshadow that was discovered last year, then this would only lead to a loss of privacy. You wouldn't need any, you wouldn't lose any keys. So this is something where you have a sort of a trade-off that you say, okay, I'm now able to use a lightweight client. However, there might still be the small possibility that this environment gets broken at some point. Or otherwise, if you don't want to have this trade-off, then you can still use a full node. yeah, this is just a small thing about the latency for requests. So at the bottom we have the interval for which we request the blocks, and on the y-axis we have the time that we require to actually build this response and send this to the client. And most of this, or roughly half of this, is actually overhead that we would have in any case that we don't really add. So what we have is basically this ORAM operations, which is the largest part of the overhead, which is roughly half of the time. But we can still basically create a response for a time span of 24 hours within a few seconds. So the overhead is is quite reasonable. All right. So to summarize, we have the first SPB lightweight clients for shielded transactions that allows us to keep privacy. This has a very low overhead, so this is practical. This can be used in without having a large overhead because of some expensive cryptography. However, one of the drawbacks is that in order to use this, you need to trust the manufacturer of the trust execution environment. So usually this would be, or currently the most used trust execution environment is Intel SGX, which would mean that you need to trust Intel to not be malicious and sign forged keys. Okay, that was it. I'm now open for questions.
You said that there was a small possibility of a complete break of these trusted execution environments. What makes you say that that's small? Because there have been several complete breaks already.
Yes, so this I guess depends on how you look at the probabilities. So I think the probability that there is, or let me start differently. So for something like foreshadow, this completely breaks SGX because you can basically create false quoting keys, which allows you to emulate such enclaves. But this means that in order to break it, you cannot retrieve old data. So basically what you have is, at that point, you could create a node that allows you to break privacy from that point on. And if there is such an attack, this would only work until it gets public, because after that you can just stop using this. So this is sort of, I guess, the trade-off there. Because you have this interval between the vulnerability being discovered until it gets disclosed where it can actually be exploited, and for sessions that happened before that, you cannot really go back if it's an attack such as foreshadow. There might be other attacks where you could recover it even if you have some memory dumps of all of these sessions, but I think it's a trade-off where you need to basically consider efficiency versus privacy, and either accept the risk that something like this might happen or go with full nodes.
Okay. So I think this is really great work. Thank you for sharing. I worry that for some users, waiting 5 seconds for every 24-hour period is going to be a little too slow. So I'm curious if you've looked at ways of pre-computing these responses to make that a little faster.
So the thing is with pre-computing, you could do this if you store the viewing keys for a longer time. The way we designed it so far is that basically with the request you send the viewing key. You could also store these viewing keys in the enclave and basically then prepare these responses on the go and send them back once the client connects, which would make it faster. Another way is, I can maybe go back to the slide. Another way is to actually connect in shorter time intervals because this is not linear. So if you request 24 hours, it doesn't take twice as long as for 12 hours, but it takes slightly more because the complexity of the ORAM adds more than a linear overhead in terms of the time required. So if you request shorter time intervals, you actually get an overall shorter time for the responses.
Thank you.
All right.